Today we have the benefit of hearing from Professor Lee on the topic of the difference in difference method. His work has not only shaped the way we approach causal inference, but also has practical implications that extend beyond academia and impact public policy and decision making. As we gather here today, we are fortunate to have the opportunity to learn from his expertise. Without further ado, it's my great honor to introduce Professor Myoung-jae Lee, who will present basics of difference in differences and triple differences. Please join me in extending a warm welcome to our distinguished guest. Professor Lee, you have the floor.
Oh, well, thank you very much for the nice introduction. Since we are a little late, let me get to the point and get started on this topic. I think difference in differences, abbreviated either as DD or DID, as you can see here. It's one of the most popular, widely used approach in policy analysis. And in this magazine called Economist, some years ago, they looked into the question on which is the most popular approach in policy analysis. And they did some search using NBER working papers. And then they found DD is the most popular, followed by regression discontinuity, and so on. In fact, DD has been most widely used since year 2012. And here are some references you can refer to. However, somewhat surprisingly, not many recent references on DD. If you want to implement DD, you can use any of widely available econometric or statistical softwares, such as Stata or R. So availability of software is not an issue for DD analysis. In typical DD, you need a qualification variable, Q, or eligibility, to receive the treatment, or policy or program. Okay. So you have a panel data, and this Q1 group, which I will call a treatment group or just T group, they receive the treatment or policy at some point in time. Whereas this Q0 group, control group, or the C group, they get never treated in your panel data. In a way, DD is a generalization of before and after BA. That is probably the most basic causal analysis method. In DA, same subjects are compared before and after treatment. Facial plastic surgery is probably the best example. You just compare photos of people who had received this surgery before and after. The critical identification condition for BA is that there should be no change without the treatment. Okay. That's the main assumption behind BA. So for that reason, when you compare photos before and after, usually the time span is very short, right? Otherwise, the facial look may change for reasons other than the surgery itself. So as written here, if treatment effect takes a long time to manifest itself, then what happens is that other variables, some observed as some not observed, denoted as epsilon, they may change during the time. Then it becomes difficult to find the treatment effect because the change in Y may be due to changes in X or in epsilon, not necessarily due to the treatment. So what DD does to remedy this problem in BA is that DD finds a control group, C group, that probably experienced the same effects due to XO epsilon, but not the treatment itself. So DD is essentially a BA of the treatment group, which contains the treatment effect and time effect. Here, time effect refers to effects due to XO epsilon. And DD subtract control group BA that contains only the time effect from the BA of the T group that contains both treatment and time effects. So the result would be ideally just show treatment effect itself. But there is a critical condition that the time effects included in the first BA is the same as time effect included in the second BA. That is the main assumption needed for DD. Yeah. So here is here's an example for DD. Long time ago, California they passed a law called three-strike law, which states that if a person is convicted 3 times, I guess for felony, then the person will be jailed for life. So one way to assess the effects of this three-strike law would be comparing the crime rates of California, say, 1 year before and 1 year after the law. Okay. If we do that, we are just looking at before and after. Okay. But in this BA, the span is 2 years before and after, 1 year before and 1 year after. During the period, other things can change. For example, the California economy may improve, then typically the crime rate drops. And another possibility is that there may be law for alcohols and it may get toughened, and which then also will lower the crime rate. So the issue is how to separate true treatment effect from these. So one way to do this is using matching. So you find the state that is close to California in the sense that the state experiences the same change in the economic or other time conditions. And one example could be Washington State near California. So supposedly then crime rate before and after California has both the economy and three-strike law effects whereas crime rate before and after of Washington State contains only the economy effect. But by taking the difference of the two BAs, actually, that is the DD, we can find the desired effect of three-strike law. And as you can see, since Washington State is selected for its economic conditions being similar to that of California, we can say that DD combines before and after with matching. Here is a famous example for DD. A long time ago, there was an incident called boat lift over this period. The issue was that immigration of cheap labor is often blamed for unemployment. That is why. And during this boat lift incidents, Miami unemployment rate increased by 1.3%. So the question was then whether this increase in unemployment rate, whether this is due to this massive influx of cheap labor from Cuba. So Card used this CPS data, which is repeated cross-sections, and he found 4 control cities, Atlanta, Houston, LA, and Tampa. They are selected because they are thought to be similar to Miami in terms of their economic situations. And yet these cities did not experience any influx of cheap labor forces. And using CPS, here are some BAs and DD. If you compare Miami, which is the treatment group, before and after, you can see unemployment rate has gone up 1.3%. And the control group average, that is the average of these 4 cities, it went up from 7.3 to 12.6. So the BA of the control group is 2.3%. So the control group BA is even higher than the treatment group BA. So DD is this number, treatment group BA minus control group PA, which is minus 1.0. So if anything, actually, unemployment rate has dropped, surprisingly. Okay. Although this number is not significant because the standard error is 2.8. So if you divide this number by this standard error, then you get an insignificant result. So the point is that just looking at treatment group before and after can be misleading. That's why I guess DD is popular. So as you can see, as you just saw, DD requires at least 2 periods. So DD analysis can be done either with panel data or repeat cross-sections. I'll abbreviate repeated cross-sections as RCS. And differently from panel data, in RCS, every year you draw new individuals from some data set. So although panel data and RCS both have many waves, in RCS, new people they enter a new wave. Of course, panel data has the advantage that it shows individual past and futures. Whereas in RCS, each individual appears only in one way, so you don't have any past or future information. DD identification conditions are easier to explain with panel data. But when it comes to estimation, RCS is simpler because you just apply OLS or IV to RCS. Whereas in panel data, you have to know how to handle panel data sets. Okay, getting to more specific, more detailed explanation of DD, I will consider two periods, T2 and 3, with qualification being time constant. And I'll assume the treatment is applied only in the Q1 group at T3. In fact, this qualification variable can be time varying because many government policies, they are conditioned on time varying variables such as income. If your income is lower than a certain level, you are eligible for some public assistance. And in that case, Q will change year to year. Okay. Nevertheless, I'll assume for a while that this treatment qualification variable is constant. Because if Q changes, the effect of Q change can confound the treatment effect. That is, when you see an effect, it may be due to the treatment itself, or it can be also due to a change in Q, or if Q changes over time. So I'll address time varying qualification in my second lecture on Monday. Okay. So today I'll just assume constant Q. You may wonder why I consider periods 2 and 3 instead of 1 and 2. There are a couple of reasons. I want to avoid confusion with these numbers for Q. And also it is possible that lagged outcome Y1 may be used as a regressor in period 2. And yet another reason is that later on today, I'll look at the difference of DD over T2 and 3 and DD over T1 and 2. So for that, for these reasons, I'll consider periods 2 and 3 for a while. If there are more than 2 periods, what can happen is that individual treatment time may differ. For example, in the United States, the federal government mandates the states to implement a certain policy. But the federal government allows each state to choose their own timing, okay? Because states, they are very different in terms of their economic conditions. Then what happens is that some states adopt the policy early in the mandated periods, whereas some states adopt the policy very late. And in DD literature, that is called staggered adoption, staggered entry. That complicates DD analysis a little, although staggered adoption, it has received a lot of attention in the recent literature. So I'll address staggered adoption in my second lecture on Monday. And today I'll mostly assume treatment timing is the same for every subject. Although in later part of today's lecture, I'll allow this timing to change across individuals. If you have more than 2 periods in DD, you can do a couple of things more than the basic DD with 2 periods. One thing you can do is that you look at the past periods across, you compare past periods across treatment and control groups to check out how similar they are in terms of, say, economic conditions. So that's the benefit that you get if you have multiple pre-treatment periods. If you have multiple post-treatment periods, then you can check how treatment effects vary over time. I mean, policy effects, usually they change over time. It will be rare to see a constant effect despite time progresses. So if you have multiple post-treatment periods, you can verify, you can estimate time-varying effects. Anyway, these are extensions of this basic setup with only 2 periods, time constant qualification. So I'll stick to this basic framework for a while. The hallmark of DD is that treatment takes its interaction form. So treatment variable D for person I and time T is the product of Qi times this indicator function of the period being 3. So for this variable to take on 1, both variables should be equal to 1, right? So you should be eligible, you should be qualified, and then the time should be post-treatment period. Following the usual notation in causal analysis, let Y1 be the potential treated outcome for subject I at time t, and Y0 is potential untreated outcome. With these notations, I can rewrite observed outcome this way. If you write this way, if treatment is 0, y equals y0, and if treatment is 1, y equals y1. So since nobody is treated at time 2, observed y is y0 for everybody. However, in time 3, if Q is 1, observed y is treated outcome. If Q is 0, observed outcome is equal to untreated outcome. A couple more notations here. Increment of y is denoted this way, delta y. And also increment of potential outcomes will be denoted in similar way. And in panel data, some regressors, some covariates time constant, such as gender or your birth year, they are time constant. But there are also many other time-varying covariates, such as income, where you live, number of children, and so on. Although I address this case only, there are some cases where treatment is not exactly equal to this product. Namely, this happens. If this happens, then I mean, when in this case, usually we just apply OLS, panel data OLS, or cross-section OLS, depending on whether the data set is panel or RCS. In this case, you can apply IVE, instrumental variable estimator, where this interaction term can be used as an instrumental variable for the treatment. But again, this is a digression, and I'll stick to this basic framework today. Now, let me express before and after using these symbols. So going back to the plastic surgery example, this will be the change in your facial look for those who receive the surgery. Okay. So this will be BA of the treatment group. This will be the BA of the control group, those who did not receive the plastic surgery. Yeah, this is DD. So DD, this part is BA, okay. The first part is BA of the treatment group. Second part is BA of the control group. And the difference is DD for periods 2 and 3. So the critical step is that
I think something happened.
okay.
Right now, you can continue.
So written in this way, now I assume the second line is 0. That is the critical DD identification condition. The second line being 0, it means that without the treatment, both treatment group and control group, they would have experienced same change in the outcome. So that's the main critical assumption in DD. So you can imagine comparing photos, say, 10 years apart. So just before the surgery, and then 10 years later, you have this another photo. So you look at this BA. Obviously, your look will change, but then you cannot say the change is entirely due to the surgery itself, because there is this huge tenure gap. So what do? You find the control group. Okay, they will provide you their photos 10 years apart. Under the restriction, under the assumption that a control group's facial look change over the 10 years is the same as treatment group facial look change over the same period. So that is what this assumption requires. So if this holds, then second line is 0. And if you look at the first line, which is reproduced here, you can see that y to 0 with minus sign is cancelled by y to 0 with minus plus sign. So what remains is y31 minus y30 given q1. So DD defines effect of treatment in the post-treatment periods for the treatment group. That actually is well known. identification finding of DD. So in simple words, if you apply DD methods, you will be estimating effect of policy at the post-treatment period on the treatment group. So going back to the plastic surgery example, you will be finding effect of surgery by just imagining what the person's look would be like at the post-treatment period, and their effect on those who receive the surgery. And this assumption that untreated outcome change is the same across two groups is usually called common trends or parallel trends. Okay. Sometimes it is called same time effect or same trend assumption. Let me show you this graph. This is an example of DD study, and these people they analyzed effects of bike sharing scheme on public bus ridership in New York. You see, these days, if you go to major cities, you can see these electric scooters and all these strange transportation modes. And you are concerned. You want to know whether introduction of those things affect bus ridership in cities. So New York City, they introduced those bikes in June 2013. That's this vertical line. And this was done in New York City, southern Manhattan, that includes Wall Street. So southern Manhattan is the treatment group. And control group is northern Manhattan, that includes Harlem. Okay. And so the upper line, it shows bus ridership change over, I think, over the months before the treatment timing. And the lower line shows the same for the control group. And although I use the term parallel trends here, it does not mean these two lines are straight. Okay, it just means that two lines can move up and down. The requirement is that the vertical difference should stay the same. If this vertical difference the same constant over time, then you say parallel trends hold. And you can see parallel trends seems to hold. However, you can near this treatment timing, the gap seems to be narrowing down a little. Like this looks a little smaller than here. But anyway, if you assume the gaps stay the same, the vertical distance is maintained. After the treatment timing, you can see the Manhattan bus rider drops, and they nearly overlap with control group outcome around here. So this figure graphically shows that effect of this bike sharing system reduces public bus ridership. Okay. The reason I put up this figure is that this almost demonstrates what parallel trends means. Okay, it does not necessarily require two straight lines. It just requires vertical difference being the same. In fact, the reason that this parallel trend is a little violated near the end is because this figure does not control covariance. Okay, if you control covariance, then actually you get almost you get parallel trends that holds almost. So as written here, in applied papers, you can see that the outcome paths of the treatment and control groups are presented graphically to demonstrate that this condition holds before treatment actually starts. Now, let me go back to BA, before and after. That is the treatment group outcome at period 3 minus outcome at period 2. Then this equals this, because for the treatment group, Y3 outcome is treated, but Y2 outcome is untreated. And I rewrite this such by subtracting this counterfactual and adding it here. This is a counterfactual because for the treatment group, Y3 outcome is Y31, not Y30. Nevertheless, we are imagining Y30 here. So this is a counterfactual. So here I subtract and add same counterfactual to BA to rewrite BA in this way. Then BA identification condition is that without the treatment, the facial look change would be 0. That's the BA identification condition. And under this condition, this BA becomes this. That is the same as DD. If you go back to DD, what is identified is the effect at the post-treatment period 3 on the treatment group. And BA, in fact, identifies the same thing here. However, the condition, this identification condition of BA is restrictive. And this is unlikely to hold if you compare two photos 10 years apart, right? Then this cannot be true. If you compare two photos like a couple of weeks apart, this is okay. So what DD does, DD allows this condition, this expression to be non-zero. In DD, this can be non-zero as long as this is the same as this, whatever this number may be, as long as that is same as the same number for the control group, then DD can identify this effect. So in that sense, DD generalizes PA. As I just mentioned, the parallel trend is critical for DD analysis, but sometimes you may not have good control group, so you may not have this parallel trend to hold. Then what you can do is, instead of usually you just take the simple average of the control group, but instead of this simple average, if you do weighted average, then parallel trend may hold for that particular weighted average. So as written here, if some linear combination of controls, if they give a parallel path, then they may be used as a single synthetic control. Synthetic control, it is called synthetic in the sense that it's not the actual or real unit, real subject. It's kind of artificial control subject. And that's why it's called synthetic. I will explain synthetic control approach, not today, but on my second lecture on Monday. This approach has been receiving a lot of attention in recent years. Now, so far I have been explaining DD using conditional indifferences, but in actual application, you use panel data linear model such as this. If you look at this panel data model, you allow this time trend over time, and then this will be a group effect. A group effect is to capture a systematic difference between treatment and control group. Okay, so this will do the job. And this part is the treatment effect part, because treatment is defined this way. So you get treated when Q is equal to 1, and then the period is same or greater than treatment starting time in tau. And these are covariates, other regressors. And delta is unobserved error that is the same over time. And this is the error that may change over time. Sometimes your treatment may not last. Sometimes your treatment just happens in one period and disappears. Such an example appeared in shopping voucher programs in China, Taiwan, and Japan. This is for Taiwan. This is, I think, in Japan. To boost the economy, the government, they 1 year just give out money to their citizens. And what is the effect of just simply giving out money in 1 year? That would be one-off treatment. In contrast to lasting treatment like this. But anyway, I'll look at this kind of lasting treatment, not one-off treatment. In panel data estimation, people are concerned about endogeneity of treatment due to the relationship between treatment and unit-specific error. So what people do, they take difference on this to remove this unit-specific error. If you do that, you get first difference model. And if you difference this model, you have a difference of trend. And this group effect will drop out because this does not change over time. And this treatment term, if you take the difference, since Q is constant, delta applies to this indicator, and this is equal to this. So this model becomes this first difference model, and you either apply random effect estimator to this label model or fixed effect estimation to this difference model. If you are not familiar with panel data, if you know only cross-section OLS, what you can do is that you can average entire pre-treatment periods to get one averaged pre-treatment equation. And then you also average all entire post-treatment periods to get single post-treatment average equation. So you end up two equations, and you take the difference of those two equations, then you get only single equation to which you can apply OLS. So the reason I'm mentioning this is that you can do DD estimation even if you know only OLS. Because in this operation, you are turning entire panel data into a single equation. Oh, here is a generalization of this Bayesian model. The generalization is that here I allow effect to change over the duration since first treatment timing. So if you look at this term, treatment timing can change across subjects. And if A is 0, you are looking at treatment effect in the same period when the treatment started. If A is equal to 1, you are looking at 1 year after the treatment started. If this is 2, you are looking at 2 years after the treatment started. By using these multiple treatment dummies over time, you can estimate different treatment effects since treatment starts. Here is a variation of DD. So far, I looked at DD as a difference of 2 BAs. In South Korea, 2018, when new government came in, they started minimum wage increase in January 2018. So the issue was then how to find the effect of this minimum wage increase. People were concerned about increasing price level and drop in employment rate due to this minimum wage increase. Suppose you simply look at January 2018 price level and December, 1 month before, December 2017 price level. Then this Y is treated and this is untreated. So this is the BA, 1 month gap between these two. Now I subtract and add this counterfactual January 2018 untreated outcome, subtracted and added, and this comes here and this comes here. So the BA stays the same. The BA identification condition would be that these two are the same. If that is true, this BA will identify effect of minimum wage law on price level in the January of 2018. However, this assumption that these two are the same is problematic because there is a seasonality. People behave very differently in December, maybe because of Christmas. This is year-ending months, and whereas this is year-starting months without Christmas. So requiring these to be the same is implausible due to seasonality problem. So what we can do to improve on this BA is that you use DD with two time-wise BAs. So instead of simply looking at this, you go 1 year back and you subtract this BA. This BA is for the same months, January, December. But there is a 1 year lag, 18, 17, and 16. And under the next assumption, this time-wise DD can identify this effect in January, just like here. And the ideal condition is that untreated outcome difference between January 18 and December 17 is the same as January 17 and December 16. So the untreated outcome change over these 2 months is same as 1 year before. That is more plausible because this is not subject to seasonality problem. I mean, if there is a seasonality effect, that would be the same. I mean, it's more likely that would be the same as this. So this DD assumption is better than this PA identification assumption. Here is a DD example about daylight saving time. You see, as far as I know, the daylight saving time started in the US by Benjamin Franklin. I heard he started this to save energy. So the question is, I mean, but this caused a lot of inconvenience among, general people who actually who traveled, across continents and so on. So this daylight saving time, in DST, you move clocks forward in the spring and then back in the fall. But the question was, does DST actually save energy? And in this study, they addressed the question using DD. Okay, in Indiana has many counties, and northeastern part of Indiana, they adopted DSP in 2006, whereas all the other counties in Indiana already had DST. So the northeastern counties are the T group, and the other counties in Indiana, they are the C group. So what these people did, they collect data on electricity consumption. And they compared the treatment group before and after. Okay. So treatment is adopted in 2006. So this is after, this is before. And electricity consumption went up by this much. That's what T group PA shows. But if you look at the C group, the other counties who already adopted DST, their PA is the PA is this. Okay. So the difference so T group, they ended up using more electricity than this control group. And so the DD is this. So what this study showed is that instead of saving energy by adopting DST, T group actually spent more energy. Again, so looking at DD instead of simple BA is beneficial in finding the true effect. In this particular study, there is one unusual aspect because the C group is always treated, which is opposite to never treated. In the usual DD, C group is never treated. And we compare T group to that kind of C group. But in this particular case, C group is always treated because they already adopted DST. So this is called DD in reverse. And if you look at the literature, you can find similar cases in these studies. For example, in this study, they are looking at effect of building a bridge for a region along a river. Okay, there is a big river, and there is one region who recently had a new bridge. So what's the impact of new bridge on the regional economy? And they compare that treatment group with other regions with bridges already. So in that case, the control groups are already treated, as in this example. And DD in reverse will be also addressed, not today, on the Monday second lecture. I mentioned that DD can be done with panel data or RCS, repeated cross-section. Now I'll briefly explain RCS models. In RCS, you have this variable indicating when the is sampled. Okay. So if this is equal to 1, the subject appears, person I appears at T3. If this is 0, the person will appear at second year. And what is observed is Q and this sampling indicator. And covariate will be either W2 or W3, depending on whether you are sampled in second period or third period. Also, Y is either Y2 or Y3, depending on the sampled period. And almost always we assume sampling dummy is independent of all the other variables in the model. If you have more than 2 periods, you can write this way, Wi, Yi, where SIT is equal to 1 if the person is sampled at period T. So anyway, the point is that in RCS, depending on when you are sampled, you are revealing different period random variables. From this underlying panel data model, I showed this panel data model just some minutes ago, and you can going through this kind of summation process, you can derive RCS model that looks like this from this panel data. And in this RCS model, you have this sampling dummies, and then this Q is here, and D is equal to this. So your treatment dummy is equal to qualification dummy times whether you are sampled after tau or before tau. If you are sampled after, you are actually treated with Q being 1. If you are sampled before tau, then regardless of Q, you will be untreated. So that's why a treatment is defined this way. So by doing OLS of Y on the sampling dummies, Q, TW, you can estimate a treatment DD effect as the slope of this D value. And if you want to allow duration varying effect and subject varying timing, you can start from this panel data model and derive the corresponding RCS model, and you can apply OLS to RCS model. That will be OLS of Y on sampling dummies Q, and these treatment dummies showing how long ago you are treated in each year. So then you can, so with this, you can estimate TD effect using ICS data. Okay, now we get the triple difference. Triple difference is a generalization of DD where the qualification itself is interaction of two. Namely, for example, suppose one qualification is that you have to be an ethnic minority. Another qualification is that you have to be a woman. So the education program is applied only to women in the ethnic minority. So the qualification variable is product of this and this. So treatment can be written in this way. Treatment is G times Q times this time domain. Whereas in DD, you have the single qualification. If you like, you can generalize TD even further to quadruple difference, namely your qualification condition is product of three domains. This can happen. Like many government policies have a number of conditions. Okay, maybe you have to be female, your income has to be below a certain level, or maybe you have to reside in certain region and so on. I thought applications of triple difference is relatively rare, but when I look up this paper in Econometrics Journal Appendix, I was actually surprised there are so many applied papers for triple differences. Since we are running out of time, I'll just see. Let me get to the empirical example first. Then I'll talk about identification conditions and so on. So in this paper, AER 2009, they applied triple difference to find effects of including tax in the price tag or not. You see, if you go to a restaurant, sometimes the price in the menu includes tax, sometimes not. Okay. If not, you pay tax extra when you check out. Okay. So the question is whether, people know how much extra tax they have to pay when check out. So rational individuals would behave the same whether tax is included in the pricing. However, many people are not so calculating. So including tax in price or not can influence people's behavior. So that is the issue here. And to find out whether tax is included in the price or not, they apply TD. In their experiment, one store, I guess it's a big supermarket in a national chain in one city, that's Q1. Q0, there are two other same stores in nearby cities. And then what they did, for certain products, that's G1, they displayed price without tax and then price with tax included. Whereas control categories, which is all the other categories in the shop, displayed only price without tax. So they compared sales quantity before and after. I think for this treatment category, this tax included price is displayed for 3 weeks in near the end of February to mid-March in 2006. So if you compare the sales before and after, this treated category sales actually declined. Control category, almost no change. So the DD for Q1 group, this one store in national chain, is this minus this. So there will be DD effect of displaying price with tax included. Now you go to the control group, 2 other stores in nearby cities. So this category, if you look at before and after, almost no change because nothing was done in these stores. In the control group, again, almost no change. And DD for this control group is 0.06. So you have 2 DDs and triple difference is this difference minus this DD minus this DD is minus 2.20. And here is a standard error. So this number is a significant decline. So contrary to people being rational, if you actually include tax in your price, sales will drop. That's what they showed. By the way, this category is, I recall, it's like men's cosmetics. I mean, in the US, the fashion for men's cosmetics is almost negligible. Okay. No man, hardly any man buy cosmetics in the US in this period. The reason was when they did this experiment, they approached a store manager to conduct this experiment. But obviously, the manager was reluctant to allow this because he kind of knew if he does this, sales will drop. So obviously, manager didn't like it. So reluctantly, he allowed this experiment only for men's cosmetics. Here, let me point out one aspect. Since this DD for Q0 has nearly zero effect, in fact, this TD effect is same as this DD effect for Q1. And this shows that TD, in this particular study, TD is unnecessary. You can just do DD for Q1 group, comparing these two categories. And same is true for DD versus BA. When you do DD, you do 2 BAs, right? But the second BA can be 0. If second BA is 0, then 1 BA is enough instead of DD. Here are some identification conditions for TD, but I'll skip that because you may find this tedious. Yeah, let me explain what happens when parallel trends are rejected. In applied studies, this kind of panel data model is often used. If you look at this model, this part is to capture control group trend changes over periods. Okay, so these are time dummies. And by using them, you capture a control group trend change over entire study period. And this is the group effect. And here you allow group effect to change before the treatment timing. So by using 1, 2, 3, 4 terms like this, you are in fact allowing pre-treatment trends across two groups to deviate as much as you like. Okay. And this part, Q times time dummies after the treatment period will be treatment timing is the treatment effect that is allowed to vary over the duration of the treatment. And people set up a model like this and test for parallel trends by setting up this null hypothesis. But here it says that all these slopes are 0. Okay. If these are 0, treatment group trend differs from control group only by this constant. So that's what parallel trend says. So you test this, and if this is accepted, you go ahead and you claim that this is the desired treatment effect. But the question is, what happens if you reject this hypothesis? So your parallel trend is rejected, then nothing can be done. That is the question. Okay. If this is rejected, you can still apply this panel data model by parametrizing trend difference. So for example, going back here, by using this term, you allow trend difference to take any form. But here, I replace this term with a linear function of time. So the model becomes this. And with this extra term, I allow control group and treatment group trend difference to be a linear function of time. So if this is positive, the trend difference can diverge. And if this is negative, your trend difference can converge. Okay. So if you use this simpler model, common trend, parallel trend can be tested by this slope of t times q being 0. Okay. So here, as written here, you can test for parallel trends with this null hypothesis that beta q2 is equal to 0. And so if this is rejected, you allow this term, and this can be still taken as a treatment effect. Let me explain by graph what adding t times q means. Suppose this is the outcome in period 1, 2, and 3. So this is the control group path. And this is the treatment group path. If you use just DD over period 2 and 3, since control group path is this and treatment group path is this, in DD, you will be looking at this, you will be presuming that without treatment, the treated group path will look like this. Okay, this goes parallel to this line. So this point will be untreated outcome for the treated group that is a counterfactual. And comparing this to the actual point, the DD effect will be equal to this vertical line G to I. That is written here. The DD will regard this vertical difference as the treatment effect. However, if I take if I use T1 outcome, you can see that from T1 to T2, the untreated paths are not parallel. Okay, you can see the parallel path will be this, but actual path is different by this much. So from here to here, you extrapolate this pattern to here. Okay, so that will be extension of this line, and this is how you allow treatment to diverge by this much. So noticing that common trend fails, but assuming trends difference can diverge linearly in this way, you take this account in constructing counterfactual here. So in when you take this into account, actual treatment effect will be H, vertical difference from H to I. So this is what T times Q does. This is what relaxing parallel trends assumption does in finding true treatment effect. So finally, today's last topic will be generalized differences. You know, in triple difference, I compared DD of one group to DD of another group. If you remember here, DD of one group and DD of another group over the same time period. But instead of that, I can look at DD of period 2, 3 minus DD of period 1, 2. This is another way of making triple difference. So if you use this triple difference, the identification condition to find treatment effect, it looks like this. You see, in this condition, left-hand side is the DD ID condition. DD ID condition is that the left-hand side is equal to 0. But in this generalized DD, ID condition is that left-hand side is equal to the right-hand side, so that the left-hand side does not have to be 0. So the DD ID condition that left-hand side being 0 is relaxed in this sense. It doesn't have to be 0 as long as this difference is same as this 1 year previous difference. I think you can appreciate this condition better in this kind of actual linear model. Suppose untreated outcome is a function of Q and T times Q. So if I take the difference on this model, I have delta YT0 and delta beta T, and this Q drops out, and the last term will be just beta Q1 times Q. So here, if I compare mean difference given Q being 1, Q being 0, the mean difference is this. So in this model, DD-ID condition is violated as long as this beta Q1 is not 0. However, generalized DD allows this to be non-zero as long as these two are the same. So if you go further, you may allow a quadratic term of function of t. So you can allow quadratic function of time multiplied by q, and that actually can be entertained by quadruple difference, not just triple difference. There are two ways to allow non-parallel paths, to implement GDD. One is that you may use regressor like this, t times q, as an extra term in your model. Alternatively, you can difference the model once or twice. If you difference this once, you can see that constants drop out, and this t times q becomes just just q, and the treatment term becomes just this. And the differencing at time 2, it'll look like this. This is similar to this, except that there is no treatment term here. And that will be differencing once, and it will be, if you difference again, differencing twice, there will be this equation minus this equation. Then you have this expression. So the question is whether you use a level equation or first difference equation or second difference equation, and in each form, where you find your treatment. In DD, under the assumption that this kind of term does not appear, treatment effect is the slope of Q in this first difference form. In generalized DD, desired treatment effect is the slope of Q in the second difference form. If you go third difference, then you still find beta D as slope of Q, and this approach will be quadruple difference. So as you do more differencing, you allow terms like this, t times q or t squared times q and so on. So in short, you can apply GDD by adding extra terms such as this, or t squared times q, and so on. And that's one way. And the other way is that you keep differencing your model until you feel comfortable that terms like this all drop out, and then you do OLS. And these two approaches have these pros and cons, as in random effect and fixed effect approach. The fixed effect approach has the advantage of allowing for endogeneity more easily, but then you lose time constant regressors in fixed effect approach. Whereas if you use this kind of level model, you will have more endogenous problem of your treatment or other regressors. but then you keep time constant values. Okay, this is the final slide, the empirical analysis of GDD. In South Korea, the government started new service for severely disabled people in Korea. So Q being one means the person is severely disabled. Control group, they are disabled but are not severely. And the goal is the finding effect of this new at-home service for the severely disabled people that was implemented in 2013. Its effect on life satisfaction. You see, because why is life satisfaction, the outcome is ordinal. It says very satisfied, a little satisfied, neutral, unsatisfied, very unsatisfied. So outcome is ordinal or not cardinal. So we applied ordered probit to implement the DD and GDD. So in DD, here is the result for DD. And this is the group effect, and this is the treatment effect. We find the group effect to be much negative. I mean, obviously, compared with non-severely disabled people, the severely disabled treatment group, treatment group has overall much less satisfaction of our life. And the treatment effect, the slope of D is 0.09, significant. Okay. This is T value. However, when we allowed this T times Q to take into account possible violation of common trend, this is what we obtained. The group effect is still negative, and this is more negative than in the DD model. And this deviation, the treatment difference, turns out to be positive, and this is significant. And the treatment effect takes a negative number, but this is insignificant. So this shows that significance of this shows that the parallel condition does not hold. And this false positive effect is due to omitting this variable. And we searched for the reason why this is positive, why this satisfaction trend for the severely disabled people went up. And then we found out that new disability pension started a little before the treatment started. So because of this, this common trend violation occurred, which we were able to capture by using generalized DD relative to usual DD. Yeah, that's about it. Yeah, today. Oh, questions? Yeah, I don't know. I brought too many slides today, so near the end, I maybe went too far. So, but yet, if you have any questions, I can answer.
So thank you very much for your interesting, useful, and inspiring presentation. So inspiring for my colleagues who work in the Department of Economics, especially on social policy. Actually, I was wondering that how can we determine different policies effects on labor market at the same time? Sometimes, actually, I mean that the government can implement many policies at the same time, and it means push on all buttons at the same time. And for instance, in Turkey, we have a good success in terms of the formalization in the labor market. Employment ratio that has been decreased from 32% to 11% in non-agriculture sector, but the government implement more than 25 social sector contribution incentives, different regime, different part of Turkey, and so different policies also, like automation, like increasing in inspection and enforcement, and so how can we determine? It seems to be impossible for us actually, but I think we need a more reliable data.
I mean, if you take many different types of drug together, then that's then impossible to separate the effects, right? Yeah. So only way is that you should look for a certain group that took only a part of the drugs. Otherwise, that's impossible. Yeah. A similar problem occurs, like in Korea, if you retire at age 65 or something, many benefits happens at the same time. And people try to separate those effects, and that's impossible. You know, you need some group not taking all those treatment at the same time.
Thank you very much, Professor Lee, and welcome to our state and university. We're really pleased to see you here. I'm Professor of Finance. We have some type of problems in finance as well. For instance, we have announcements in the market, financial market, like merger announcements, dividend payment announcements, as well as we have also policy shifts or changes in finance. For instance, in 2004, there's a policy change in international financial reporting standards. In other words, it is actually the accounting standards, a change in the accounting standards. So to see the effect of those type of policy changes, we apply event studies to our articles or data. Here we try to find out the impact of the changes by using the methodology of event study. This methodology may be a good approach for us in finance, and we can apply this to our data as well. What I want to know is that are there any specific properties for choosing control groups, because this is important for us? And what is the optimal horizon for the timeline after the policy to see the policy effects? Because we know that from the event study, if you increase the event window, it will affect your analysis. So what's the optimal horizon for that? Is there any time horizon or optimal horizon for your key methodology here?
Well, I don't know whether there is any optimal horizon. Let me address the question of finding control group first. It really depends on your study. I mean, in some cases, finding control group is easy. For example, you saw this bike sharing system in New York example today. In such an example, go back to this. I mean, for transportation policy, typically transportation policy is applied locally. But then it's easy to find control group, like this. Here, this policy is applied, say, one part, southern Manhattan. Then it's easy to find control group. But so in this kind of case, it's easy to find control group. For the minimum wage example, people use typically some industry supposedly not affected by treatment. If you work in finance industry, probably your wage is already too high if you are not subject to a minimum wage. Like accounting rule change, probably some firms are not affected. Although the law applies, generally to everybody. I don't know, but some industries, some firms are not, for some reason, not affected by that accounting rule change. Then they will become controllable. So yeah, you have to look for, law and rule. I mean, laws are, in principle, it applies to everybody, but for some reason, as in the minimum wage case, some firms are not affected, and you use them as a control group. And about this horizon, the more you go into the future, it becomes more ambiguous, right? Because other things change. So definitely, as time progresses, it's more difficult into the future to find the effects. Because you are talking about things, I mean, policy that happened a long time ago, how it affects today. So everything depends on finding a good control group. I mean, going back to plastic surgery, if you compare 10 years apart, 20 years apart, 30 years apart, it's getting more difficult to find effect of plastic surgery. But if you find identical twins, then things get easier. So everything depends on how good your control group is. Yeah. So if you can find good control group, you can get good publication. It's done over. Yeah, it will open. And we should announce that this is what it's coming.
And we thank Professor Lee for his informative presentation.